Thanks for the wonderful introduction. Thanks all for coming here. Let's get started. The title of my presentation is Exploring Relational Features and Learning Under Distant Supervision for Information Extraction Tasks. So, the goal of information extraction is, given some unstructured text like this, to be able to extract some structure out of it, like identifying some entities and relations between entities and so on. Why is this a hard task? Because there are lots of issues like entity disambiguation, entity resolution as it's called, then type disambiguation, then some of the facts might not be current in the database, then there are also such type of cases where the Washington inside Washington Post should not be marked as a location. Okay, so the way we look at it, look at information extraction is that of finding patterns in data. Suppose we are given a set of basic features like a dictionary of first names or last names and so on. To identify entities, we would have to form combinations of such basic features like a first name followed by a last name and so on. Some of them are like simple combinations like these that I am showing. Some of them are not so trivial combinations. For instance, a span of text is an organization if it matches an organization rule and does not overlap with a location and so on. So, there are many such patterns and we would like to explore this space well. So, we use induction to actually explore this space of patterns, which is what we term as data driven patterns. Then on the other hand, for relation extraction, if the setting is something like suppose we are given a large database of facts like Freebase, and we have a large corpus. This is the distant supervision setting where it's a noisy alignment process, and here learning relation extractors is adding some kind of constraints to the training a part of relation extractors. For instance, a mention of a pair of entities expresses at most one relation, or it could be a fact present in the database is expressed at least once in the corpus, or it could be something like some of these semantic constraints like the prime minister relation. The first argument has to be a person, so called selectional preferences, and a few more. So, there are not many such constraints and they are more intuitive, and that is why we term them as user specified patterns. So, the high level summary of the work is as follows. So, we have information extraction tasks. Among that, we have these two tasks of learning for named entity recognition and for relation extraction. In the named entity recognition part, we work in the paradigm of relational feature space exploration, which is further we will look at what relational feature space is in some time. So, in this paradigm we would like to learn feature combinations for generating rules, and use these feature combinations also in a statistical system and see how it performs. And for the relation extraction part, we work in the paradigm of distant supervision, where there are like many of these constraints and we would want to relax some of these constraints. That is one setting. The other setting is we have reformulated the training as a max margin setting, and we would like to optimize for multi-variate performance measures for reasons that we see later. So, this is like the high level overview of the talk. For the purpose of this talk, I will focus on the first and the last aspects of the works. So, what is feature space categorization? Why is it necessary? So, existing work in feature induction does not have too much of a focus on information extraction tasks. So, our categorization is inspired from how one authors NER rules manually. So, let us see an example of a relational feature. So, our examples are encoded in this kind of a first order logic kind of setting. It is a definite clause where a span of text like we have has a head predicate which is the label. It's a textual span X, and it has some subspans, and there are some relations between these subspans. That is why they are called relational features. So, these predicates are called relation predicates, and there are some properties of these spans and subspans, like you have the subspan comes from a first name dictionary, or it matches a capitalized word regular expression and so on. So, these are termed as basic feature predicates. So, while we define a lot more classes, the hierarchy of the classes, for the purpose of this talk, I will just focus on two classes. The first is the one that I sort of alluded to you in the beginning of the talk. So, this is like the candidate definition features, which is basically these first name followed by last name kind of features, some kind of chain kind of features. This is one class of features that we are looking at, and the second one is these kind of refinement features, like a span of text is a location if it does not if it matches a location rule and does not overlap with an organization rule, like for instance this Washington inside Washington Post example I was talking about. And by the way, just feel free to stop me at any time so that I can take questions if there are any. So, having seen that, let us go into learning rules using in this kind of a rich feature space. So, existing systems do not focus on a rich rule language like the one that we saw here, and our induction system is as I told you before, is how it's closely modeled on how NER extractors are manually written, and we define the notion of rule complexity to be able to measure interpretability as a proxy, interpretability of a rule. So, rules can get very complex. So, this is part of a person named entity extractor written in a declarative rule language, and this achieves the best performance among this is the state of the art for NER. So, it is very complex, and building it from scratch is hard. So, can we
this is a pretty small font, can you give us a sense of some of the complexity?
Yeah, so yeah, it's deliberately in small font because the rules are built on top of each other. It's like there is one view, there are like a couple of views which are combined together, like first name followed by last name. These kind of rules are put together, and then these are all unioned together, and then you subtract them. This is like a SQL kind of query. So, you have views, each of them is like views. There were like for this named entity extractor, there were like 600 or 700 views that were built over time, one on top of the other.
I guess off the top of my head, I would say that if you have a lexicon of first names, which can be very large, and a lexicon of last names, then some simple rules over those two lexicons would give you something pretty good. So I'm just trying to understand what's here and why it's better. So you said there's 600 views, but what are these views giving you?
Like for instance, one particular example that I can think on the top of my mind right now is something like in the Enron corpus. It's like a lot of the email conversations have a lot of list of names, right? And then there are like multiple rules that can be triggered, like a first name followed by last name can be triggered, or if there is a list of names like this, then you have like a last name comma first name also being triggered. So, there are multiple such patterns. So, you would have to like engineer these kind of exceptions, so to speak. So, you have like a rule and you have like an exception for that rule and so on, and you would want to keep some of the dictionaries like separate. You do not want to merge dictionaries. It could be dictionary of surnames, or it could be dictionary of say US based names and things like that. So, something like that. Yeah. So, specifically the problem statement is as follows. So, suppose we are given as input a set of basic features in the form of dictionaries and regular expressions, we automatically construct the predicates that we saw before. And we are also given an annotated document collection which contains these annotations of person, organization and location. Our goal is to induce an initial set of NER rules that have a competitive accuracy and that have low complexity. We will define what this complexity is later in the talk. And the loose connection is a rule having a low complexity is interpretable. Of course, this is questionable. There can be a lot of debate on this. So let's see how a nameless extractor is built manually. So we have like these, first we identify some of these basic feature predicates like a capitalized word or a first name dictionary and so on, and then we form these simple combinations. Then it turns out some of them will not be right, so you would have to add some filters. So those are the candidate refinement features. Then you have like multiple rules, and you would want to like consolidate them in the sense that there could be multiple overlapping spans that are annotated by a rule, by a set of rules, and we would like to keep we would like to use some kind of consolidation policy. It could be like a contains within consolidation or an overlap consolidation or things like that. So finally we have the extractor built. So our induction system is sort of like closely modeled on this process. So we are given as basic our basic features and the annotated data set and a simple consolidation policy, and we semi-automate parts of the pipeline. The first is the definition of candidate, first is the automation of the candidate definition features. We induce these CD rules, so to speak, using techniques from inductive logic programming called least general generalization, which I will get into in a minute. And at the end of this process, we have we construct what is an attribute value table, which is used in a propositional rule learner to learn the refinement features that the refinement rules that I talked about before. This is like the high level overview of the system. So least general generalization. So just this is explained with an example here. The idea is very simple. It is like we are given these predicates and we take two examples and we want to generalize, find the general predicate that generalizes these two examples, and it is just like the intersection. It is the least upper bound of the given pair of clauses. So one thing to note here is that there are many paradigms of names. Like for instance, there could be a first name followed by last name or a first name initial last name and so on. So it makes sense to actually do some kind of clustering beforehand, and LGG is some kind of a recursive operator that we can operate on each of these clusters. Otherwise it would result in not so good generalizations. So we do some kind of clustering before on the body of the clauses, of all the clauses, and then we form an LGG rule or a candidate definition rule from each of these clusters. So yeah, at the end of this we have we construct this span CD table, which is like explained with an example here. So as columns we have the set of all candidate definition rule names from the previous stage, and the rows are the set of all spans returned by every CD rule, and then we have like as cells whether a rule generated a span or it generated an overlapping span or it did not generate that span, so on. So we build this kind of a simple a table, and then we also have the class labels, and this is used in a propositional rule learner. We specifically used a Ripper in Weka to actually learn these kind of rules that I showed you before. Yeah.
So you don't have any notion of uncertainty or confidence or probability? Is that right? So these are kind of logical rules.
There is some notion of uncertainty as well, which I sort of did not cover in this part. Yeah, I have it here. So like we know that clustering is suboptimal. So so what we do in the system actually is we perform this this clustering iteratively, as like in a separate and conquer technique. We have the notion of a good cluster, and then we select the good clusters and remove all the examples that are entailed by the good cluster, and then we do the clustering again, something like that. So there is this notion of variability. And then one more thing that I abstracted out is our target rule language is annotation query language, which is like SQL, and this is developed by people from IBM research, and they have like a system text, just like how there was system R, there is system text, which is like an engine to run the AQL, which acts like a theorem prover for our system. So we would have essentially have to generate lots of these candidate definition rules, and to explore this space it turned out to be a very fast system, very fast theorem prover. So that is why we used this kind. So there is expressivity in terms of a declarative language, and there is speed in terms of system T. So
I'm sorry, I'm a little bit confused. So separate and conquer, right, is a property of Ripper, right? And Ripper is not a clustering algorithm; it's a classification algorithm. So I'm a little bit confused between the three things. And neither clustering algorithms nor Ripper represent uncertainty explicitly, which I think is what Peter was asking about. So let me ask the following questions: are you representing uncertainty explicitly in the form of a probability or something else?
okay, so I should have made it a little clear. I had like some extra slides. So this iterative clustering is in the first stage. Like if we see here in the clustering and LGG phase, there we are doing iterative clustering actually, and not in the second part of the system.
So you're doing separate and conquer twice. First in the clustering phase, and then
yeah, so yeah.
Okay, and where is uncertainty represented explicitly?
It's not. Yeah, it's not. Uncertainty is not explicitly represented.
Okay.
Like so, we have this notion of a good cluster, which is what is the precision of the rules that were induced by the cluster. So we sort of have like a cutoff, and we select only those kind of candidate definition rules which have like a which cover like a minimum number of examples. These were like input to our system. Sorry, parameters to our system.
So I apologize if you went over this and I missed it. The part that I'm finding confusing is where exactly do the labels come in? So you're doing clustering, which you typically do on unlabeled data, and then you're doing classification. So when do the labels come in?
Yeah, that's a nice question actually. So the clustering is done to actually identify various paradigms within a particular entity. Like I talked about these different kind of person entities, right? There are various ways in which person names can appear. So clustering is done in that part, not for, I mean, of course it's a supervised learning setting where we are actually given the labeled data.
I see. So have you done an experiment that compares just running, say, Ripper on the data and running Ripper with the clustering first to presumably pre-process it to make it easier for Ripper? So it would seem that's an unusual choice. It seems like it might help or it might not.
Right. So yeah, we did not do this particular experiment, but we did do a couple of other experiments about how can we incorporate bias into the system, which maybe not related to what you are asking, but yeah, this particular experiment we did not do. Yeah, so yeah, I was talking about this notion of bias actually, which basically tries to incorporate the expertise gleaned from manual rule development to guide the induction process. And we have this notion of extractor complexity, which I'll explain. again it is a simple notion where we want to induce rules which manageable complexity is what we started out with, and it is to also reduce the search space of our algorithm, and the expression is actually inspired from database literature where we measure the length of a rule. To be very specific, like the length of the number of views in the from clause of an SQL query. So, it translates to a length of a basic feature rule or a consolidation rule is 1, because there is only one of them, and a candidate definition rule has a number of basic feature rules, and the length is the number of that, and similarly candidate refinement rules. And the final extractor complexity, the sum of the lengths of each of the rules. So, yeah, so moving on to the experimental setup, we ran it on the standard CoNLL dataset train test, and there were 3 experimental scenarios. The first one was we wanted to see how what would be like a baseline. We used a very small set of basic features to see how the system performs in comparison with manual rules, and we enhanced this set of features with more domain independent dictionaries and regular expression rules to have this other scenario, which is E2, and then we have a domain customized set of features, like in the CoNLL domain. A lot of country names have been tagged as organization because they occur as sports teams. So, we added those kind of features to see how best the system can perform if we are given a domain customized set of features. So, yeah, so we have the E1 scenario. This is like the F score 48.5, and the final extractor complexity, that one number. So, that is that, and like when we added more features, domain independent set of features, we saw like an increase in F score, mainly increase in recall, and consequently the final complexity of the extractor also increased. And it is the same story with adding domain customized set of features. So, we have like the best score among our 3 scenarios, and it also has like double the complexity of the final extractor. And another thing that we looked at is comparison with the manual rules. So, the E2 setting is exactly the same like in our induction setting. Some of the basic features we actually got from the manual rule set itself, and here it is domain independent set, then it was customized for this CoNLL domain, and the accuracy is the F score is in the 90s, just like any statistical system. And our systems like have around 70% of the max F score. But if you look at the complexity of the final rules, we ran exactly the same procedure to compute the complexity, and we see that there is like half, the complexity is reduced by half.
How well does a supervised learning system do on this? Like if I just trained a CRF, what would I get?
It's around 90%. Yeah, I think the best system on CoNLL dataset is Roth's, and I think it's CoNLL 2009, and it is like 90.1% or something. F measure. Yeah.
So it seems the obvious question, right, that seems like the CRF-based version does a lot better than the relational. What am I missing?
Yeah, so this is something that I keep getting on and off. So, why are we doing something which does not beat the state of the art? Our goal is not when we started out this work, our motivation was not to beat the state of the art, but to actually come up with an initial set of rules that could later be tuned and improved upon. Because starting from scratch, building an initial set, building from scratch the extractor is like, it takes I think close to 6 person months or something to actually do that. So we were trying to see if we can use induction to actually reduce the effort in doing this, but that part was like outside the scope of the current work. So of course it needs more HCI kind of experiments to actually validate this claim.
What takes 6 months? The manual?
The manual rules, yeah.
But we're talking about a learned version, right? So
right.
There's a learned version, and you're proposing a different way to build a learned version. So why,
right.
The two be compared?
So again, why should we go for manually authoring NER rules? Is there are two reasons for this. I think so. One is like, if you want to customize it to a new domain, then you would need new training data, more labeled training data. And two, more importantly, we want to have some kind of a provenance. So suppose there is like you discover a false positive or a false negative, to correct a machine learning based a model based system would be hard to do debugging in some sense. So that is the reason why we would want to author NER rules, but then authoring rules is like pretty hard. And can we build tooling around it, like a declarative rule language which will help in things like determining the order of when the rule should be applied and so on. Those kind of issues will not be there if there is declarative syntax of rules. That is like the overall motivation. How are we doing on time? So yeah, so I'll just maybe quickly skip over these slides. So relation extraction, identifying relations between entities, and traditionally supervised learning is not scalable. In literature, people have looked at distant supervision to leverage existing databases to learn relation extractors. And this is the idea of distant supervision. You try to heuristically align the facts in the database to the sentences which contain the mentions of the entities in the corpus. And in particular here we are looking at a training regimen where we formulate it as a max margin training setting, and we optimize for multi-variate measures. The reasoning is that generally in literature, distant supervision systems, the training is optimized for conditional log likelihood or error rate or such objective, and it and the evaluation measure is like F score or something. So there is like some kind of a disconnect between the training objective and the evaluation measure. Hence, we sort of push for this multivariate performance measures to be optimized. And further, can we provide like a knob in training to favor one over the other, like say precision over recall, something like that. So these are the two motivating factors of this work. And our approach is like, it's a large margin method which contains and to learn the parameters, it contains latent variables, and we optimize for multivariate measures. And the approach in a nutshell is that it interleaves convex concave procedure with dual decomposition. CCCP is used to populate the variables, the latent variables, and dual decomposition is used to factorize the hard optimization problem during training. And the model that we use is the multi-R model from Hoffman et al. 2011. where it's essentially a Markov random field with two types of variables, random variables. The first is the corpus level relations that we get from the database, and then there are these hidden sentence level mention labels which are hidden. Yes, they are the latent variables. And there are two types of factors, the local sentential factors, and then there are these aggregate factors which help in determining the aggregate relation given a set of mentions. So, some more preliminary. So, this is for one data point in our training data set, and we define the set of all data points by this capital X, Y, and H. And in structured prediction learning that we want to do, the goal is to find a parameter vector W that minimizes this risk, which is given as a function of loss over your predictions and the true labels from the training data. And most large margin methods assume that the loss is decomposable, hence the empirical risk actually is defined for individual data points, individual losses. However, if we want to optimize for non-decomposable losses like F, we can't do this process. So, the training objective is like this. So, we have the regular struct SVM kind of objective, with the difference that there is a capital delta term there which does not decompose over the individual data points. So, and this objective is non-convex since it is a difference between two convex functions, and this is solved via a convex concave procedure. So, it is some kind of an iterative procedure. I will sort of give you the top down view of things. First we have to do this training thing where we have to this is an iterative procedure where we maximize the latent variables given the current weight vector, and then we have the other step wherein given the assignment to the latent variables we solve for W, which is similar to this struct SVM kind of cutting plane algorithm to solve that. And this convex step, which involves solving for the cutting plane to find the best W, involves this loss augmented inference, which is what we are interested in. And this is over all the training data points, it does not decompose. So, we employ dual decomposition here. We form a Lagrangian to find to decouple the two terms in the loss augmented inference like this. We form a Lagrangian which has like these two independent subproblems, which now there are these two loss terms, two Lagrangian terms. One is what we term as the loss Lagrangian and the other is the model Lagrangian. And this Lagrangian is an upper bound on the original loss augmented inference, and we find the tightest upper bound by minimizing this, and this is solved via a subgradient descent method. And the individual Lagrangian, so the multivariate loss, that is what we are interested in first and foremost, which involves the loss, the delta term there involves all the predictions and all the true labels from the training data, and all the predictions, I am sorry about the font there. So, the set of all possible predictions is exponential because it is a multi-instance, multi-label learning setting. And but however, we can express the predictions and the true labels in terms of some kind of aggregate statistics like false positives and false negatives, which we can use to actually compute the loss. Even then, it is a hard problem because there are lots of points. So, this is like an integer. So, both false positives and false negatives form like an integral grid, and there are lots of them, and we want to like do this fast. Doing it exhaustively was like taking a lot of time. So what we did was we used a simple local search kind of algorithm, which is like a greedy way to solve this. So we have like on the z-axis we have the loss, which we can calculate from for any point on the grid. We can calculate the loss, and we calculate the loss of one point and all its neighboring points, and like pick the one which has the highest, and then do this in a greedy hill climbing fashion, and we stop when we are not able to proceed further. Now this simple optimization actually led to several orders of magnitude speed up, and in some small scale experiments that we did, the performance did not degrade so much, but we had like several orders of magnitude speed up.
Can I ask a question? Can you go back a slide? Isn't this optimization problem just as hard as your original optimization problem? Like, what are you getting from the dual decomposition?
You mean
Go back
this
more.
one? You mean
Yeah. Because you're maxing over y prime, and you have a linear term here, and you have a thing over there, and you've picked the h's already, right?
you would still not be able to guess. No, for the given set of y prime, finding the set of y double prime is not easy, right? That is why we need this kind of constraint that needs to be introduced in the middle. Okay, yeah. So the other Lagrangian is the model Lagrangian, and this is like map inference on undirected graphs, and we use ILP formulation, which we relax to LP to actually solve this. And coming to the experimental setup, we use the benchmark data set by Riedel et al. 2010, and the baseline was a multi-R, and we have two approaches. One is the max margin learning approach with that optimizes for a decomposable loss like Hamming, and the other is the max margin approach that optimizes for this F loss, which is non-decomposable. And some results. So on the Riedel data set, we see precision recall in F. This is our baseline, Hoffman, and then we see using max margin thing with decomposable loss. I am sorry about the numbers. Actually, it is, I think it's 74 or something there. I am sorry about that. I saw that while coming here, I forgot to update it. So yeah, so we see that there is some drop in precision, but there is an increase in recall for this method, and there is an overall increase in F. And for the non-decomposable loss, we see that there is like an even balance between precision and recall here. The overall F improves by around 8% points. So 8% improvement, 8 to 10% improvement is there compared to our baseline. And so we saw that it was more geared towards recall. So we wanted to see, and one of our motivations was to see if we can optimize for precision instead. So this is the approach. So we have the F which is weighted, the weight that we provide to F for precision was 0.8, and this gave like an improvement in the final precision numbers of this thing. So this is like the summary, and what we did not cover is like how do the relational features perform in a statistical setting, and also what happens when we relax some of the constraints of distant supervision and other works, and some like very briefly, I'll just try to cover my current research focus. It's fine-grained entity typing. So standard NER is over a very small set of types, and there has been a lot of recent work on using a much larger set, and it is shown to improve a lot of downstream tasks like question answering, relation extraction, and so on, using a fine-grained set of types helps. So we would like to extend this to very fine-grained set of types like thousands or 10,000s of types, which can include textual appositives as well. And there is already some work from our lab which uses universal schema to actually do this kind of a thing. So universal schema tries to learn a latent representation of the types by doing some kind of a matrix factorization over and learns these vectors in a low dimensional space, which some of the labels come from structured knowledge bases like Freebase, and some of them can be textual appositives which are extracted from free text. And when we learn vectors like this by doing matrix completion, we get very good representations for latent representations for the types. Additionally, we also want to model context dependency. So given a mention of an entity, say Obama, and the types of Obama in say DBpedia, there are many such types, but for a given sentence like this, we would want to predict the relevant set of types for this mention is book author. We would want to select a subset of types, not all the types. And suppose there is another sentence which says that Obama is a smoker and it is not even part of the knowledge base, we would want to extract these kind of types as well. And this is again very preliminary work, and the way we are approaching is to use neural network based approaches using attention mechanisms to do this fine-grained typing, and using novel embedding techniques. Again, another work from our lab which is quite interesting and which can be applied, and we want to apply this to this task, is to be able to learn instead of learning single points in vector space, can we learn like a density, like can we learn map a Gaussian, and the reason for doing this is twofold. One is if you want to measure the breadth of a concept, like say composer, there is some sort of uncertainty over it, but if it is a person there is more uncertainty. Composer is less uncertainty, it's less it's more well defined, so on. And also this sort of asymmetry between things like is a relation, right. So a composer is a person, all things like that. So a person is not a composer, and this has been shown to do very well on unsupervised lexical entailment. And another work that I have started recently that we are very excited about is doing question answering in a hierarchical manner using hierarchical neural architectures. The idea is given a question, can we like drill down to answer the question like from a set of textbooks to the actual textbook to the chapter to the particular paragraph to the answer. So to do this kind of, to devise this kind of a hierarchical architecture with attention mechanisms at various phases, and this is again some very preliminary work, and acknowledgements to my collaborators and my advisors. Thank you.